Okay, here's our quiz for the day. And of course, if you're doing this as a district student, go ahead and do the quiz, but now I'm gonna do the solution, okay? You wanna work it before you see the solutions. And people did pretty well with this. Okay, zeros are the numerator. There's the numerator, you set it equal to 0. And this splits into two equations. With obvious solutions. Now you can just look at this and see what the solutions are. But when you do this, I want you to write this out because sometimes these are going to be more complicated equations and you're going to have to solve them. And you're going to have to understand that you're not going to be able to see what the solutions are until you do the arithmetic, do the algebra. So you split it into two equations because if two things have a product of 0, one of them is going to be 0. Okay. And if neither one of them is 0, it can't be 0. Because you can't multiply two numbers that aren't 0 and get 0. All right. Now the 0 is the denominator. Very simple, x plus 3 equals 0. And you get a solution. X equals -3. Y-intercept. When x equals 0. So you get y equals 0 minus 5 times 0 plus 2 over 0 plus 3. That's -10 over 3. If you're going to put it on a graph, you probably want to see that it's -3 1/3. Okay? I think that's pretty much what everybody got. Now, we put these in a graph. Now, I didn't tell you to sketch the graph because there's something you don't know, or unless you've learned something about rational functions. And I don't think we said much about it in this class. I have to draw the line x equals -2, put a point on the x-axis. Because when the numerator is 0, y is 0. Okay? So I can say and that also occurs when x equals 5. Now, 0, the denominator, occurs when x equals -3. That's not an x-intercept. So if you drew that as an x-intercept and then drew a curve through, well, that's great. That's what you do with polynomial. But don't do that anymore. Okay. It's not an intercept. 0, the denominator, is something completely different. And that's not familiar to us yet. So let's get familiar with it. Okay. near x equals -3, the graph is like, let's see. I should have said y equals, but it's like 8 over x plus 3. What's 8 over x plus 3 look like? It's just your 1 over x graph, reciprocal graph, shifted 3 units to the left and vertically stretched 8 times. Okay, now we should know this, but at this stage of the course, these things are still a little bit fuzzy. It's like this, which means it's going to go up like here, and it's going to go down here. Because the reciprocal graph does that. It has an asymptote to the y-axis. Your toolkit reciprocal graph. As x gets smaller, y gets bigger, right? Or maybe in the negative direction. Okay, so it acts like this. So it's basically like a reciprocal function. So this is a vertical asymptote. The y-intercept is at -3.5, y equals -3.5. So let's go ahead and draw for -3 1/3. Draw a line for y equals -3 1/3. Got to go through this point. So somehow it comes down from here, goes through this point, goes through this point, and comes back up here. That makes sense? Again, the way to understand what happens near x equals -3 is to understand that when x is close to -3, where did I get 8 over x plus 3? When x is close to -3, x minus 5 is close to -8, right? And -3 plus 2 is -1. So -8 times -1 is 8. That's where I got the 8. I just said if x is -3, the numerator is 8. And if x is close to -3, it's close to 8. So this function is close to the function 8 over x plus 3. You don't absolutely have to know that. You can use some kind of superstition with numbers and calculators, and OpenMath will probably tell you to do that. Okay. Now there's more to it. There's what you call a slant asymptote. So I'm going to calculate that, but that's easy because you know how to do long division. Okay. So far we've got this. I'm in a quandary here. Okay, I've got this much room, but I need more room than that. So I guess I'll move the camera. We'll get this kind of thing straight eventually. Okay. Numerator has degree 2. Meaning if I expand that numerator, I'm going to get x squared minus 3x minus 10. Okay, I'll expand that and we'll do that. It's going to be an x squared, meaning the degree is 2 because the degree is the highest power you see in the polynomial. And the denominator is degree 1. So if I divide the numerator by the denominator, I'm going to get a linear function. Let's just do that. If I multiply out x minus 5 by x plus 2 using the distributive law, I get x squared minus 3x minus 10. And dividing that by x plus 3, well, let's see what I get. We do x plus 3. This one's pretty short one. We get x. X times x plus 3 is x squared plus 3x. It looks like that would give us 0, but of course, we got to be careful. Put a little auxiliary sign in here to show us what we're really doing. Since we're subtracting this from this, we're actually going to do negative 3x minus 3x, which is negative 6x. It's minus 10. Okay. Then x goes into negative 6x 6 times. And we get negative 6x minus 18. Put our auxiliary signs here to make sure we don't mess up. We have a remainder of 8. So we could say that's x minus 6 plus 8 over x plus 3. Now the x minus 6 is going to dominate this function if we zoom out. So we're zooming way out, so negative 6 here would be practically at the origin. There's the y equals x minus 6 graph. Okay. Now, as I said before, what we've got is y equals x minus 6. But in here, there's some wiggles. You know, right there, it's wiggling a little bit, right? Okay, so it wiggles. Since it's going to approach y equals x minus 6 for big X, in other words, when we get out of the wiggle range, we draw the x minus 6 graph here. Okay, so if negative 3 1/3 is here, y equals negative 6 would be about here, wouldn't it? Seem about right? Okay. And we have a slope of 1. And here's x equals 5, so x equals 6 would be here. So I'm going to sketch a graph like this. Right there is the graph of y equals x minus 6. So what's going to happen with this graph? Comes down here, goes to this point, comes up to this point. Maybe it rises a little, but then it starts just falling off and starts approaching this y equals x minus 6 line. Didn't leave myself enough room here. This is a little bit of a mess, but can you see what's going on there? We come down from this asymptote, go through this 0, hit this y-intercept, then we got to turn around at some point and come up here. Once we're through here, if we're still going up a little bit steeply, we've got to turn around and come back down. Now, I can't tell you right now whether it even does something like this. I'd have to take derivatives and do some calculus with it, which is not difficult once you know the calculus, but you don't want to see it. Okay. And I don't want to take the time to do it. All right. Now, the other thing is what happens over here. Because the thing comes down from this asymptote here, it goes right through the x equals 6 line, and it comes back up here. What's it going to do? Well, I didn't give myself enough room. I'll do another little sketch. But it's going to turn around at some point. It's not going to go through 0 because the only place it can be 0 is at this point or this point. Okay? Because the only way it can be 0 is for the numerator 0. The only way the numerator is 0 is if x is one of these values. So it doesn't come up as far as the numerator. Maybe it doesn't even come up this far, but it starts turning around and then it just approaches this line. Okay. So if I want to draw a little better picture, it doesn't take much to improve on the one that I just drew. Let's draw it in. Okay, so again, we have this. We have a 0 here. We have an asymptote here. We have a 0 here. We have a y-intercept here. And we have a line to which the graph has to be asymptotic. So my label for y equals x minus 6 is kind of in the way. I'm going to relabel it. And let's get rid of that so we don't confuse it between the two graphs. So again, what happens? We come down from here through this point up here, and then we approach this line as an asymptote. So right there, possible curve. We come up from the negative side on this thing, and then we turn around and we approach this line from the other side. Okay. Yeah, I probably didn't draw that exactly right. Again, it takes a deeper analysis. Got to see what's going on with the derivatives and stuff. See where the peak of this thing is and all that stuff. Okay. Again, something that's pretty easy once you know calculus. But we can't do that here. All right, so this would be the graph of approximate graph y equals r of x equals x minus 5 times x plus 2 over x plus 3. And I'll just say, just for scale, here's x equals 5. Here's x equals y equals negative 6. And from these, you can kind of estimate what everything else is and see that the graph is fairly representative of the function. All that makes sense? All right, you all are doing well. So we have this function. We follow the usual pattern. And we write it out, even though we can see it, we write the dang thing out. Because sometimes you need to do that and you want to be in the habit. You don't want to get in a situation where you can't see what these zeros are. And then you don't know what to do. If you write out the equation, you find that x equals 4, or x equals -6, or x equals 7. So if we've got our graph, got to figure out a good place to put the graph. Guess I'll put it over here. We already know that at x equals -6, at x equals 7, and at x equals 4, we at least tentatively have zeros, as long as the denominator isn't also 0 at one of these points. We're safe saying that these will all be zeros of the function, giving us x-intercepts. Okay, and we can see very clearly that the denominator is not going to be 0 at any of these points. You wrote the denominator, you want to write out the equation, even if it's trivial. Then you find that x is -2. I think everybody's got that. Vertical asymptote. Y-intercept. Curves from y equals r0, 0 minus 4, 0 plus 6, 0 minus 7 over 0 plus 2, which equals 84. You know it's not -84 because you got two negatives and the rest are positive, right? So you want to be careful because sign errors are really easy to make. I made them. Okay, so we got y equals 84. We're going to have a line for y equals 84. It's written badly because the board is wobbly. It really needs to be written better. I'm sorry. Y equals 84. It's kind of small. I don't believe that's readable. Meaning here's our y-intercept. Okay, so what's the graph look like? Well, as it turns out, that's a good one. It'll come down through here, turn around and go to this asymptote. And I'm actually going to draw it, then I'll tell you why it does this, okay? So we start up here. Come down here, nice and graceful. And then it acts like 1 over x because it's like 1 over x plus 2 with a vertical stretch. It's vertically stretched by whatever the numerator is when x equals 2. Okay. And That's all I'm gonna say about that for the moment. Okay, well, your vertical asymptote, since the y-intercept is up here kind of high, since I drew it kind of high, I could have drawn it lower. But it's gonna come down from here, go through here, come down here, come back up here, and then just go right on up. And that's kind of what the graph is going to look like. Now, why does it? Here's the long run behavior. Well, first of all, the numerator is x minus 4 times x plus 6 times x minus 7. Now, if I multiply these out, I get x squared plus 2x minus 24 times x minus 7. And that's going to give me x cubed. I've got to be careful. I'll have negative 7x squared plus 2, so I have negative 5x squared. And x's, I'm going to have negative 14, negative 24, negative 38x plus 168. 7 days a week, 24 hours a day, 168. So I know that's right. Okay, 168 hours a week. This is the numerator. If I expand the polynomial, in the numerator, that's what I get. And it's over x plus 2. I know if I divide this denominator into this numerator, I'm going to get an x squared, right? So you can even write I can even write this, and I'm going to have an x squared here. That's going to give me an x cubed plus 2x, etc. All that really matters is the x squared. Is the x squared, when x gets large and you zoom out, x squared is so much bigger than any of the other terms. If you square a big number, you get a much bigger number, right? X squared is going to dominate. Open math tells you the same thing. Okay. So zoomed out, you're going to have like the x squared graph. Well, I don't have to draw that very big. Zoom out, your graph is going to look like this. Going to have the x squared shape, again with wiggles in the vicinity of the origin. Here are your wiggles. Here's the overall shape. Okay. The overall shape says it's got to go way up on the left. It's got to go way up on the right, which this one does. So by reasoning this out, I say, well, it goes this way and it goes this way. Okay. There's our long run behavior. It's the long run behavior of the x squared function, the function we get when we divide the denominator into the numerator. Now, open math probably gives you some superstitions about that. But you know, superstition means use your calculator to do things, okay? Or whatever. You don't need that. And that's not the way I prefer to tell you to think about it, but if that's the way you prefer to think about it, if you get the long run behavior right, one way or another, it's okay. You don't have to do it like I'm showing you. But I think this is easier to understand, because you don't have to understand the numbers very well. The way Open Math probably tells you to do it. I haven't looked at all the videos, I think, sometimes they change. And I don't know it. But they do stuff numerically. Now, I think y'all probably do have pretty good number sense, so maybe you can understand it well that way. Many of you, I'm sure, can. But you already know how to do long division. You know that the result is going to be x squared plus a bunch of stuff of lower powers, right? So the thing is going to act like the x squared graph when you zoom out. And that tells you what happens for the long run. Okay? You don't even have to do the long division. I just write this out to show you, well, if you divide this into this and you write it out like this, we are going to get an x squared there. So you can just see I've got an x cubed here and an x here. And they'll say, okay, the degree of the numerator is 3, the degree of the denominator is 1. So when you divide it out, you're going to have a degree of 2. This just justifies that whole idea. And as soon as you know you have degree 2, you know it's going to act like the x squared function. That's all there is to it. I'm going to do another example. And let me double check the time. Okay, we've got 14 minutes. It's really plenty. Anyhow, okay. R of x is x minus 3 over x plus 2 times x minus 5. Now, I'm not going to write out the details because you know how to write out the details. I'll just tell you. And it's actually just 0. Okay. That's easy, right? The y-intercept is -3 over -10 equals -0.3. Positive 0. You see what I mean about negatives? I almost made that negative. That was going to mess everything up. Okay. I wasn't doing that just to make you feel good. I just wrote it down too quickly. Okay. Expanded R of x is x minus 3 over x squared minus 3x minus 10. If we zoom out, I say leading terms are all that matters. So R of X is approximately X over X squared, X over X squared. Ignore all the rest of the stuff. It's 1 over X. Large values of X. So zoomed out. It looks like this. But we got wiggles. I'm going to make the wiggles region just a little bit bigger to show you that it doesn't really approach the y-axis as an asymptote. What we're really interested in is the long run behavior, which is it approaches the x-axis from below. It approaches the x-axis from above, this side and on this side. Okay. And then in here it wiggles. So in the region of the wiggles here, I'll just kind of say, well, we don't have this and we don't have this because we're in the region of the wiggles. So at some point it just starts wiggling. So the graph looks like this. At x equals 3, we have this. At x equals 5, we have a vertical asymptote. At x equals -2, we have another vertical asymptote. So if I want to draw the graph, oh yeah, we have the y-intercept, which is at -0.3. So we've got to, as we go out this way, we've got to approach the x-axis. As we go this way, we got to approach the x-axis. The other thing is, this thing stays above the x-axis. This thing stays below the x-axis. That's what the reciprocal function does. So we're going to follow the reciprocal function for a while. But then we got to have an asymptote at x equals -2. Okay. Now let me say one thing here. It's x plus 2. If that was x plus 2 squared, that would change things. Your asymptote would have degree 2, and it would approach the asymptote from the same side. On either side, it would approach the asymptote at the same end. Okay. So I'm not going to talk too much about that. I want to get these basics down, but that is an important idea. Okay, so then what happens? Well, we come down from here. We got to go through this point, and then we got to go through this point, and then we got to approach another vertical asymptote. That's easy enough to do. There we go. Kind of a boring curve. Okay. something's wrong. That asymptote should have an odd degree, meaning we'd have to come back up here and approach the X asymptote, and it doesn't approach it from above. But if X is a big positive number, R of X is positive, we can't come up here and go through the X axis. So I've done some boneheaded thing. Something just ain't right here. Make sure that that's negative. Remember when I wrote down the negative here and erased it? I didn't erase it out of my feeble brain. So actually, it was intentional just to show you that, you know, if you make a mistake like this, it's not going to fit. It just doesn't work. I can't get that to work. You understand why? Because this asymptote has degree 1, has multiplicity 1. From x minus 5, that's x minus 5 to the first power, means it has to act like a reciprocal function, approaching the asymptote from above one way and below the other way on different sides. Okay. So I've got to take this boring curve that I drew and I was so fond of, and I've got to make a big old correction. Now I can come down here. I'm okay to about there. We're going to forget that I ever did that. Okay, have you forgotten yet? Okay, then we going to get rid of this. And we're going to write this line, which I'll label over here, y equals 0.3. And there is my y-intercept. So I don't have to. And another thing I did was I went right through the x-axis to get to that y-intercept, right? But function isn't 0 there. It's only 0 when x equals 3. So I made a bonehead error there too. Okay, so anyhow, I come down here and then it's got to flatten quite a bit out here. And it stays pretty flat for a while, and then it just turns around and approaches this intercept here. And then it can do exactly what I thought it was going to do here. Okay. So 2 things. Beware of negative sign errors, which a couple of you made. So don't feel too bad. Intentionally made that one so you'd feel better. And I got the negative 0.3 in my head, even though I corrected it and drew it down here, and it threw everything off. I got all kinds of impossible things. So if it's impossible, go back and see what you might have done wrong or what you're looking at wrong. Okay. Okay, well, we're out of time. You haven't taken the test, get it done. I'm probably not going to be able to grade the tests until Friday, but I will look at them. So if you want to email me and say, how's my test look? I can tell you. Because I'll be looking at them this afternoon and tomorrow afternoon because people might be taking it late today. Other than that, I think you've got a pretty good start on doing the rational functions. We'll get that done before class on Thursday. And then we're going to move into exponential functions, which are kind of easier than what we're doing right now.